on. And it's Friday, February. I'm going to keep these for semesters comes, and hopefully in 2030 or something like that. One, I'll be retired. That's about when I'll be retired. I'm retiring at 70 because I'm having too much damn fun doing this right now. But anyway, welcome today. Anyway, we're going to learn about centrifugal motion. What I wanted to be able to do is show you, because I'm starting to see that a lot of you aren't. I'm not seeing a lot of people watching these things. So anyway, if you'll take a peek right here, this will be on Lecture 7 videos. Okay, and if you click there, you'll see these slides that I've made. This is from Chapter 5. I should have made this Chapter, yeah, this still, no, this is more Chapter 6. Well, let's go ahead and make that change right here. Right now, we can do that. Oh, but then I had to go back and change it inside your thing too, so maybe I'll remember to do that. All right, so anyway, it's Chapter 6. We're talking about uniform circular motion. Now, this is when we're going around in a circle in order. This is a long slog. It's 40 slides, and each one of them I could spend 15 minutes on. No, actually we could do a few problems off each one, but for the most part, you know, we're talking uniform circular motion. This uniform circular motion is when we're going at a constant speed along a path. Now, the only constant speed along a path, but the velocity is always changing. Why? Because it's accelerating. And so the velocity along the path is the speed with the speed with which it goes is equal to 2 pi r divided by the period, time. How long did it take you to make make a lap? Okay, and that's the period. Okay, now the frequency, I'm going to go ahead and talk about that right now. All right, let's get some variables out of the way before we get too far. So this is Lecture 7, and this is only good for up to Tuesday, because I don't know if you can see the entire screen, but up here it says 2:37 on a Friday afternoon. I want to leave here by 3. So I'm getting this sucker done. I'm going to do it fast. I'm going to do it badly. No, it'll be good. So if we're going around in a circle, if we make a complete trip around this circle, we know at a constant speed, we know we've done the circumference is equal to 2 pi r. Okay, where we're using the degrees in radians. Okay, now I don't think you'll have to click your calculator over to radians for this chapter, because even though we're going to be talking about radians per second, then the velocity that we're going to be going is the velocity that we're going to be going would be the speed, 2 pi r, that was bad of me, divided by the time. And they make that a capital T because to make one trip we call the period, which is equal to capital T. Okay? So, now the frequency that this thing, in other words, how many trips a second does this thing make? Or how many trips a minute does this thing make? That would be the frequency. That is equal to 1 over T. Okay? The frequency is equal to 1 divided by T. All right? Okay, now then, the angular speed, so let's let them talk about it, but I wanted you to know what these two terms are. Period is like, if I ask you what's the period in days, what's the period of the Earth going around the sun in days? 364. 365.25. What's the period of the Earth's rotation in hours? 24 hours. Now we're going to do everything in seconds. We're going to do everything in seconds. So we're going to, and by the time we're done with this chapter, we're going to come up with some crazy seconds, like we're going to, how many seconds are in a year and that kind of stuff, just to get Kepler's laws to work and things like that. I think this is cool stuff. I think it's good stuff to learn just as general science. So let's go back here. So a tire. the wheel of a tire has a radius of 0.29 meters and is being rotated 830 revolutions per minute on a tire balancing machine. Determine the speed at which the outer edge of the tire is moving. Ooh, that's the speed at which it's moving. This is a great problem. Now here's what we're doing. How many minutes per revolution are we talking about? Okay. So they're taking the inverse of, first of all, here's the way I do these problems. Let's look at, okay, 830 revolutions per minute, because we need to talk about this so that you understand this. And then I will stop this portion of the lesson. Okay, because this I think is an important thing. Okay, so they're saying 830 revolutions per minute. First thing we're going to do is we're going to turn this into radians per second. 830 revolutions per minute, we're going to turn into radians per second. Okay? And we know how to do that. How many radians is equal to 1 revolution? How many radians? Do we have that written down anywhere on this page? Yes, we do. Right there. So 2 pi radians is equal to 1 revolution. So when I have 830 revolutions, just multiply this whole thing by 830. So to get from revolutions to radians, just multiply by 2 pi. Just multiply by 2 pi. Simple as that. So I'll have 2 pi times 830. I'm not going to multiply it out right now because I don't have my calculator. Radians per minute. So I got that 2 pi. Now, I've got to take times 1 minute per 60 seconds. Because there's 60 seconds in 1 minute. They're multiplied by 1. So that cancels. So I've got 2 pi over 830 divided by 60 seconds. Which that cancels down to 30. So it's pi over 30 times 830. All right? This is in radians per second. So that is your, whoops, I need to turn off my, yes, I'm wonderful. I know that. Okay, so radians per second. That's how you do it. So what's the conversion thing? If you're given revolutions per minute, so the total revolutions per minute convert to radians per second, I think this is huge, is equal to, you multiply by pi and divide by 30. There it is. There's your simple multiple. Now, what do we mean by I'm going to stop here, and then I'm going to start with my idea of radians per second, because I think it's important that we hammer these ideas home.